Today we're talking about inverse relations. Now, an inverse relation is simply a relation that can be obtained by switching the coordinates. So given that all coordinates or all relations are listed as coordinates in the x, y, then the inverse can be obtained by simply switching around those coordinates. So your new x is the old y, and your new y is the old x. All right, in example 1, we're given a relation q is equal to -2, 5, -1, 7, 0, 3, 1, 7, and 2, 1. We want to find the inverse of q, and we're going to call h that inverse. So we're simply going to switch those coordinates. My coordinates then for h will read 5, -2, 7, -1, 3, 0, 7, 1, and 2, 1. Oh, I'm sorry, that's 1, 2. All right, well, I've gone ahead and I've graphed q in blue, and we're going to graph the inverse h in red. So take a second to plot those points. Here is 5, -2. Here is 7, -1. Here is 3, 0. Here is 7, +1. And here is 1, 2. All right, so now we have the regular relation q in blue and its inverse in red. You can see that the graph of any relation and its inverse are actually reflection images over the line y equals x. Now remember, that's that identity line. That's that line that cuts through the origin at a 45-degree angle, and it goes through all those points there. So here's our line y equals x. If I reflect all the blue points over that line, you should see that they're mapped onto their inverse coordinates, which are the red points. All right, let's try a few examples here. At the top of your notes, you have the inverse relation theorem. And it says this: suppose f is a relation, g is the inverse of f, then we can find a rule for g, the inverse, by switching x and y, and then solving for y again. We also note that the graph of g is a reflection image of the graph of f over the line y equals x, as we just looked at. And we also note that the domain of g, the inverse, is the range of f, and the range of g is the domain of f. All right, so in example 2, we want to find the inverse function for this function y equals -2x squared. So we're going to follow number 1's step here that says to simply switch the x and the y. So I have x is equal to -2y squared, and then we're going to solve for y again. So remember inverse order of operations to get y by itself. We're going to divide both sides by -2, and now we have y squared is equal to x over -2. And to undo the square, we got to take the square root. Now when we take the square root, we again will allow for both the positive and negative square roots of, that's x over -2. So we say that y equals positive and negative square root of x over -2 is the inverse function of y equals -2x squared. All right, in the next example, we're going to do the same thing. Let's find the inverse equation. So we're going to practice our strategies here. Switch your x and the y. We get x is equal to 3y minus 4, and then solve for y again. Add 4 to both sides, and then divide by 3. Our inverse equation is x plus 4 all over 3. Now you can write that another way. You can write it as 1/3 times the quantity x plus 4. These are equivalent functions. All right, in example B, we also want to write the inverse, so we'll switch x and y. And we'll start by adding, or I should say subtracting, our 8 over to the other side. So we have x minus 8 is equal to y minus 3 quantity squared. To undo the square, we need to take the square root of both sides. When we do that, we're going to allow for both the positive and negative square root of x minus 8 is equal to y minus 3. And our final step is to add that 3 over. We're actually going to add it in front, so we'll say 3 plus or minus the square root of x minus 8 is the inverse function of y equals x minus 3 squared plus 8. All right, so that's a little bit about writing the inverse function. Let's see how we can learn how to determine whether the inverse is actually a function. So recall you had the vertical line test to be able to tell you whether a particular function was a function or not. Well, now you're going to learn the horizontal line test. And it says a horizontal line intersects the graph at more than one point, then we know the function's inverse is not a function. Okay, so let's take the horizontal line test. Let's put it to the test here in our first graph. Any horizontal line we pass through the graph here is only going to touch the graph in at most one point. So we say, yes, this function is an inverse. Or I should say, yes, this inverse function is a function. Now, you'll see the difference here in our next one. Here is the graph of the squaring function. We draw a horizontal line. You'll see that it passes through that square function in 2 points. So we say, no, the inverse is not a function. All right, that's terrible spelling, but you get the idea. All right, same thing for the next one. Any horizontal line we pass through here, it looks like it's going to touch this graph in more than one point. So we have to say the inverse of this function is not a function. All right. Whoops, one final example here for today. Example number 5. We want to graph the inverse of our square function as a reflection over that line y equals x. Then give the domain and the range of both the square function and its inverse function. All right, so if we take and switch out some of these coordinates here, if we reflect it over this line y equals x, 0, 0 will still be on the graph. 1 over and 1 up will be on the graph. 1 over and negative 1 down will be on the graph. 4 over and 2 up will be on. 4 over and 2 down will be on it. And same thing with 9 over and 3 up and 9 over and 3 down. So here we have a few points that are on the graph of this inverse function. And it looks a little bit smoother there, but there you have it. This is the inverse. And you can see here if we change colors up and if we throw our y equals x line in here, here's our reflection line of y equals x. You can see that they're reflection images of each other. And we can also see that our domain here for our square function, here's the graph of y equals x squared. Our domain is going to be all reals, and our range is going to be all reals greater than or equal to 0, because it only exists up here in this top half of our coordinate plane. However, our domain and range for its inverse, which will be the function y equals plus or minus the square root of x, our domain now is going to switch and it's going to be all reals greater than or equal to 0. However, our range will be all reals. So hopefully you noted that pattern, that when we take inverse functions, their domain and ranges just switch. The domain of the inverse is equal to the range of the original function, and vice versa. The range of the inverse is equal to the domain of the original function. And that's how inverse functions operate.